Okay, YouTube, in this video, we're going to introduce the concept of tracking the position of a projectile in the air over or as a function of time. And so to kind of sketch out the situation that we're looking at here, we would say that imagine in a two-dimensional situation here, we would have our x displacement and our y displacement of some object that let's go ahead and assume will fire from the origin, but boom, out in, say, some direction. Now, when you fire this out, technically, it doesn't just keep going in that direction because we know gravity affects it, but what we get is this parabolic arc right here, but really described by this initial vector here, v. And so I'm not going to go too much into detail about this vector v, but I do want to mention just some really quick facts. I could actually describe the motion of this object by looking at the components of this vector here. And so given a vector v, which is the firing vector at which we fired this object in the air, we would know what direction this was heading in, and we actually would know its velocity or the magnitude of this vector. But knowing the velocity of this vector and the direction, we could say then the horizontal motion of this vector will be given by the component magnitude of our vector cosine theta, and our vertical speed of this object would be the magnitude of our vector times the sine of theta, given that magnitude, v cosine theta, magnitude v sine theta are respectively the x and y components of this object's motion. So that being said, what this does is it allows us actually to use a couple of parametric equations that are very common in order to describe the path of a projectile at a given time, but separately with respect to x and separately with respect to y. So I'm going to write these again, but these two equations that you see right here are going to give us the position of an object with respect to x and y as functions of time. And so we say that our x position as a function of time is always v sub 0 cosine theta, and I'm going to put that in parentheses, times time. And we're going to say that our y direction is always given as negative 16t squared plus, in parentheses, v sub 0 sine theta times time, and this is plus h sub 0. So the things that we want to write about this model are simply these. We say v sub 0, theta, and h sub 0. What are these going to represent in our situation here, in our model, and how do they affect the path of a projectile over a given course of time? So we say v sub 0 is going to represent our initial velocity. The closest analog that I can give you to v sub 0 above would be the magnitude of the vector. So it's kind of like how fast it was going at first. And then our theta here, this is going to be our direction angle. What we want to know about this direction angle is that it's in standard position. Okay, that means that it leaves from the positive x-axis, and it usually goes counterclockwise here as we imagine this. And then this is going to be our initial height, h. And so what I want you to kind of see here is this. I actually created a Desmos graph, and what I did was I made it parametric by saying, graph me the set of points that have x values of these and y values of these. And so when I put this in, you can see this up here, we see that our x value is the magnitude, or initial velocity, cosine theta times the time, where you'll notice that my theta, I'm actually using an A for angle since it's not going to allow me to use a theta here. But our y value is our initial height plus our initial velocity times the sine of our direction angle times time, minus 16t squared. You see that this projectile kind of follows this path right here. So what are some things I could say about this projectile? Well, right now, some things that I want to point out are that my initial height is 0. My angle, or my theta here, is 53 degrees with the positive x-axis, and I have an initial velocity of, we're going to say, 100 units per second, where this might be feet per second, meters per second, miles per hour, who knows? But you could track the path of this here, and we usually do it in feet per second. And so that's what I want to use with all of our situations with the parametric equations that I've given you here. So you'll notice that if I change my initial velocity, you can see that this projectile is going to go further because I'm just firing it out further. And then also when I change the angle here, if I had a shallower angle, like a 30-degree angle, my projectile may not go as far just because it's firing off at a shallower angle, whereas if I fire it straight up at 90, it's going to go straight up and straight down. And then last but not least, our initial height. So you can notice that our initial height here, what I want to point out is that it's always just our y-intercept when you look at a graph of the situation. But it does say that, sometimes, you shift it up because maybe you fired it from an initial height of 10 feet. So we have to take into account that 10 feet right there. So looking at parametric equations to describe the position of an object, what I want to do is kind of look at a situation where we talk about maybe the path of a football through the air using these two equations. So we say that a football is kicked with an upward velocity of 30 feet per second here at an angle of 55 degrees. What we want to do is consider the position of the ball at any time t if air resistance isn't to be worried about, if it's negligible. So the first thing we always want to do is just kind of come up with our parametric equations to describe or model the situation here. So some things we want to write down. First of all, I know that my initial velocity here is 30 feet per second, and one thing that we want to say about this is it is positive. Now, why do you say positive? Well, I do want to point this out. If you have an upward velocity on any of these projectile motion problems, then we're going to say that your velocity is positive. So we say if v sub 0 is greater than 0, then we're going to say upward velocity. Okay. If v sub 0, our initial velocity, is less than 0, negative, we're going to have a downward velocity. And the way I could describe that is, it would be weird, but imagine a football player or kicker kicking a ball straight downward towards the ground at 30 feet per second. We would call that negative 30 feet per second. So our initial velocity here, positive 30 feet per second, and then this angle of elevation here, this is my direction angle, so it would be a 55-degree angle with the positive x-axis. And the last thing I want to point out here is that it didn't mention anything about initial height, so our initial height is 0. So our equations to model this situation, starting with our x displacement at any given time, is going to be our initial velocity, 30, times the cosine of our direction angle, 55 degrees, and we're going to take all this times time. So really our rate of change in our x direction times time. Rate times time is our x distance. And so we say, well, what's our y displacement? Well, using our equation here, we say negative 16 times squared plus our initial velocity times the sine of 55 degrees here. We're going to take that times our time. And this would be plus 0 here for our initial height. So I'm actually going to leave off the plus 0 this time. So with these two equations here, what we want to acknowledge is that it would tell us our position with respect to x and y at any given time, where time is being measured in seconds. All we have to do is plug the times into these equations. I can tell you how far away it is in an x direction or how high off the ground it is in a y direction. So let's go ahead and use these then to try to answer some questions about the path of this projectile that we've kicked from an initial height of 0 at about a 55-degree angle here. We can say it's about 55 degrees at first, at a velocity of 30 feet per second. So looking at this kind of situation here, we say, when will the ball hit the ground? The first thing we want to acknowledge is this. What I'm asking you for is t. Now, where we see t up here is both our x value and our y value, but when we say, when will the ball hit the ground? Well, where on this picture is the ball on the ground? It would be at its x-intercepts. So to be clear here, we would say that at its x-intercepts on the ground there, to be specific, our y value would be 0. So if we're looking for what is the time when our ball hit the ground, let's do this. Let's grab our y parametric equation here, which was this, negative 16 t squared plus 30 sine, we got 55 degrees t plus 0. We're going to set y equal to 0, and we're going to go solve for our t value. Now, the first time that I usually show this to people are like, how am I going to solve for t, Mr. A? Like, that's hard to do. But when you look at an initial height of 0, it's a little bit easier to do because look at this. This is a totally factorable expression where both of these terms have a t in common. So let's go ahead and factor this by taking a t out in front. And what we get left with is negative 16 t to the first plus 30 sine 55 degrees. But that's going to lose its t. So the neat thing about this is now we've got a factored expression. And the product of two factors that equals 0 can only be true if each of its factors are also equal to 0. So we'd say either the time was 0, which by the way on our diagram up here happens right at the beginning of this projectile experiment, or negative 16t plus 30 sine 55 degrees. Either that equals 0 or t equals 0. So to solve this one for t, which is right here by the way, we're going to go ahead and take this constant because it is just a number and put it on the other side. So we get negative 16 times t equals negative 30 sine 55 degrees. And then to solve for the time here, all we have to do is divide both sides by a negative 16. So dividing by a negative 16 is going to make these values a positive again. But we get the exact time, and the exact time would be exactly at 30 sine 55 degrees divided by 16 seconds. Okay, that's when your ball is going to hit the ground. So let's go ahead and take a look at what this value would be now. To be very clear, your calculator is going to need to be in degrees here. So to check this out, I am in degrees mode, but we're going to take 30 sine of 55 degrees, and we're going to divide that by 16. So what we end up with here, sorry, let's go back and divide by 16, not 6, is we get the time 1.54 seconds. So we're going to say t is about 1.54, and you want to label this here seconds because this is what we're trying to find. So don't lose this time. This time is very important here because my next question is going to concern how far away in a horizontal direction did this ball go. So if we're talking about, well, I know the ball was in the air for 1.54 seconds. How am I going to find out how far it went in an x direction? Well, that's exactly what these two parametric equations are designed to do, to tell us how far we went in an x direction as a function of time, and how far high off the ground we are as a function of time. So as long as we have a time, we can go plug that into either of these to go find out what our x displacement or our y displacement would be. So looking at this question then, we say, okay, well, how far does the ball travel in a horizontal direction? Remember that our air time was 1.54 seconds. So what we're going to do to find our horizontal displacement is we're going to take our x parametric equation here, which is 30 cosine 55t. And we're just going to plug in for our time 1.54 seconds. So what we end up with then is our horizontal displacement is 30 cosine 55 degrees, but we're going to take that at 1.54 seconds after we started. So again, this is just a calculator situation, but we want to kind of understand what is it that I'm asking for. So we say 30 cosine 55 degrees, end parenthesis, and we're going to take that times 1.54-ish. And so what we end up with is about 26.49, I'm going to call 26.5. Okay, so 26.50, and this is in feet since we do these situations in feet here. So looking at our next question here for D, it says, at what time will the ball reach its maximum height? Now, funny story with things that are quadratic here, ax squared plus bx plus cy equals this. But when we look at these right here, we'd say that the vertex right here, if its equation is in standard form like this is written, is always having an x value of negative b over 2a. So because our vertex has to happen at negative b over 2a, what we're going to do is we're going to say, well, let's take our y equation here, which is this I suppose quadratic equation. And what we're going to do is we're going to find out what is the time at which we are at our vertex. And to do this, we're going to do negative b over 2a. So looking at our original equation, I want to write this again for you, but I don't want you to be confused about this. We had negative 16 times squared plus 30 sine 55 degrees times the time plus, and I'm going to write 0. We really have our a x squared plus b x here plus c. So in order to find the time at the vertex, we want to write this down here. The time at the vertex is always going to be given as t equals negative b over 2a. And so what we're going to do is we're just going to take our y equation here and we'll do our negative b over 2a. But what we get is this. We say our time at our vertex, the time at which it reaches its maximum height, given by negative b over 2a, would be negative b, which is our 30 sine 55t here. Negative 30 sine 55 is our b value. And then we're going to put that over 2a. So we say 2 times a, which is negative 16 here. So let's work this out on our calculator here. We really get negative 30 sine 55 degrees over negative 32. But really, when we put this in, let's see, what do we get here? So we get negative 30 sine 55, all of that divided by negative 32. We end up with the time being about 0.77 seconds. So approximately at 0.77 seconds, okay, is the time at the vertex, which really represents is at the maximum height. The time at which our ball reaches a maximum height. So what we're going to do now is we're going to say, well, if that's the time at which our ball reaches the maximum height right here, 0.77 seconds, then if I want to find the maximum height of the football, now I'm going back and saying, okay, well, now I'm using my parametric equations again. If I want to find the maximum height of the football, then I'm going to use my y equation here, but I'm going to plug in 0.77 seconds for my time because that is the time at which it reaches the maximum height. So we're going to say, okay, well, if y equals negative 16 t squared plus 30 sine 55 degrees t plus 0. Then we're going to say, well, let's let t equal 0.77 seconds, like this, squared plus 30 sine 55 degrees times 0.77 seconds plus 0 for our initial height. What we end up turning out is the height at which we reach our maximum value or maximum height. Okay, so we get negative 16 times 0.77 squared plus 30 sine 55 end parenthesis, but we got to take that times our time, 0.77. And we could even put on the plus our initial height, which was 0 here. But what we find out is about 9.47 feet off of the ground there. So that 9.47 feet, that's not very high off the ground, but why did this happen? Well, you know, you didn't kick it very hard, 30 feet per second at a 55-degree angle. And so one thing that we might even go do here is, you know, if I even go put this in, we say 30 feet per second, that would greatly reduce the amount of force that we're putting on this ball or this projectile here. And we did it at a 55-degree angle, so 55-degree angle here, and with an initial height of 0. Okay. So when we talk about where does it reach its maximum height, it's kind of hard to see here, but we'd say that, you know, this would be 5, 10, 15, 20. Right here at about, what do we get here? 0.77 seconds later, we would reach a maximum height, and that maximum height occurred at 9.47 feet off the ground. So when we go look at this picture here, we say, okay, well, 5, 10, 15, 20. It is about 9.47 feet off the ground, and that would have happened at 0.77 seconds then. So looking at these parametric equations, I'd say the most important part is that we can actually just set them up in the first place given your initial velocity, your initial height, and your direction angle, but then interpreting the questions to say, well, what is it that I'm trying to go find? Am I trying to find a time at which it's here, or am I trying to find the actual position at a given time? Cheers.